Greetings, this is Mr. Gusakuma, and today we are going to tackle exponential versus linear growth over time. This is a complicated subject that is going to incorporate several of the things that we should have been picking up along the way. So it's a synthesis of information that requires coordinating several facts together. First, I would like to review our exponential functions. We have our exponential function shape as f of x is a times b to the power of x. Exponential functions are characterized by multiplying by the same amount each time. And the letter a is going to be our starting amount, the letter b is going to be the amount we multiply by each time, and the letter x, sometimes used as the letter t, is going to represent an amount of time that has passed. Our exponent will always be an x because this is an exponential function. On the other side, we had linear functions, for which I just wrote the word line, that followed our generic equation of y equals mx plus b, where our y value, sometimes written as f of x, is going to be the sum of a starting value, which is b, that y-intercept. So again, b is how much you start with in this case, plus an amount that we add for each period of time. And that amount is m, which is slope. That's how much we change each time period. So x, again, is often used as t for a time period. M is going to be the amount of change in that time, and b is our starting value. Because the title says exponential versus linear growth, I'm going to be looking at each one of these two examples and trying to determine which one is exponential and which one is linear. So I'm looking for keywords here, things that will tell me if I'm either adding an amount each time or if I'm multiplying by an amount each time. The keywords that jump out to me in this case are the word doubles, which means we're multiplying by 2. So triples would be multiplying by 3, quadruple would be multiplied by 4, but it's a multiply, so that's going to tell me that my first example here is exponential. And the other keyword I see that jumps out at me is increases by 5 a month, and that increases here is adding. It's not by a percentage where we'd multiply that percent, but it's increasing by a set amount, a constant amount, so that 5 would in essence be our slope. That is the amount of change for the time of 1 month. So the exponential function that I'm going to use for this problem is going to be 5 times 2 to the power of x. I know that's written rather close together, but that is 5 multiplied by 2 to the power of x. That dot in the middle is very significant. That is not 52 to the power of x. The 5 in this case was how much the city had started with. It says the city has built 5 kilometers of bicycle paths. And then the 2 is going to be the amount of change, where it says it doubles each month. So that means that our x, again, is going to be our amount of time. So an x in this case is a month in this case. On the right-hand side, I'm getting my numbers by saying Tinseltown has built 21 kilometers and by the end of the first month, so that was telling me how much they're starting with. And then it says the total length of the path increases by 5 kilometers per month. So that means, again, my x is a month, and 5 is how many more kilometers we get each time. So from here, I now need to compare these two functions that I've created in order to answer the problem, the question that has been posed. To help me analyze these problems, I am going over to Desmos again, and I'm going to enter both of my equations. You can enter the y equals or the f of x equals if you like, but it's not necessary. And so I've got my Charlestown in green and Tinseltown in red. So I'm going to go look over to my graph now to figure out when green's graph gets above red's graph. So looking at the graph of these two, they both start at a time of 0, where we had Greentown at 5 kilometers and Redtown at 21 kilometers, and you would think that 21 is a lot larger than 5. But under the guise of exponential growth, where that 5 is doubling each time, and the red is only increasing by the same amount, increasing by the 5 each time, you can see that green starts to be above red, or green meets red, at 2.8, 35 and some decimals. Now remember, it is the time we are worried about here. That is our x value. That is our months in this case. So it looks like in 3 short months, or at the end of 3 months, Greentown will be way above where Redtown is. Now again, be sure you are carefully considering what has been written here. This question asks at the end of which month does the total length of the paths change, and it tells us the amount at the end of the first month. So while we graphed this using that as a 0 value, a starting value, that's actually at the end of the first month. So our 2.8 does give us a 3 months change, so at the end of the first month, plus an additional 3 months, gave us a correct answer of 4 months. So quickly walking through the next random problem I have. My first step was again to sort out which one of these is exponential and which one of these is linear. That is, which one multiplies by and which one adds by, to find the differences. So I've got an investment Q and an investment R. They have different starting values, and almost all the rest of the words are identical throughout the rest of the problem. So simply looking for a keyword like increases isn't really helping me too much in this case. But I do notice that Q, my top investment, is increasing by a dollar amount. That means I'm adding that amount of money each year, while my R increases at a percentage, and again, we do percentages by multiplying. So I know that when I'm increasing by a percentage, that's my interest rate formula, an exponential growth formula, one that tells me we're going to be multiplying by a certain amount. So the two formulas I'm going to end up here is for our linear function, a $500 plus 45x, so $500 is my start, plus $45 for each additional year. And then my exponential will be $400 for the start plus, or multiplied by 1 plus 0.10 to the power of x. So that 1 is giving me the 100%, so that's giving me everything. And then when it says it's increased by 10%, that's why I'm adding the 0.10 for each additional year. And those years again are my time, my x's. Again, on the top value, my linear function, it's multiplying by that 45 because I'm just adding that amount each year. So 45 plus 45 plus 45 plus 45. While my investment function that is increasing by a percentage on the bottom is multiplying by 1.1 every year. Our last step was to take this to a graphing utility like Desmos to be able to compare these two graphs. It lets us zoom out and look around very quickly, and I'm not going to spoil the answer for this problem if it's one you happen to have. Good luck.